Might changed.
Yeah. It's too warm. Sweaty.
Oh, it's me now. It's my turn to talk. So first of all, this section did extremely well in the test. So you scored at the same level, if not higher than UH Manoa. So good job. So, and in general, students did very well in this test. I'll give it back on Wednesday. I gave extensions for a few people that didn't show up. So give it until today, and then I'll pass them back. So no, but good job. But does anybody have any questions about anything before we start? Okay. So we're moving on, and where we're at now is in gas laws. So I know we had a bit of a respite there going back to other stuff, but now we're talking about gas laws, and now we're at the section called kinetic molecular theory. So do an analogy. Does anybody have a favorite fast food item? Anyone? Anyone like fast food? Yes?
Oreo McFlurry.
Okay, Oreo McFlurry. Do you know how many calories are in an Oreo McFlurry? I guess this is something we can ask Google. How many calories in an Oreo McFlurry? So there are 803 calories. Does that mean that every single Oreo McFlurry has 803 calories? No, it's probably more something that looks like this. And at the top here is 803. Right, so it's probably something like that, right, where you're going to have some sort of distribution in a range, and depending on how efficient your McDonald's is, right, you're going to have a various amount of Oreo McFlurries, but on average it will be about that much. So what? Well, I'm trying to relate this to temperature. So just like the number of calories in Oreo McFlurry, the temperature of this room right now is about 25 degrees Celsius. Actually might be a little cooler, like 23. And temperature is average kinetic energy. But the word is average kinetic energy. Does that mean that every single gas particle has the same velocity? No. Of course not. There's a distribution. And we'll get to that later. That's kind of with, and this is kinetic molecular theory. These are the assumptions of it. These are the postulates. And this is where the ideal gas law is taken from. So the size of particles is negligibly small. So that means that the particles themselves, they do not exert a volume. Can you guys see the screen? Is this too bright in the room?
It's a little hard.
Okay. Let me turn the lights off over here. There we go. Is that better? So the size of particle is small, so that means you can go to zero volume and the gas particles will not have any volume, just the gas itself, if that makes any sense. And the average kinetic energy of the particle is proportional to temperature in kelvins. That's easy, that's a definition of temperature. And the third part is the collisions with each other or with the walls is completely elastic, meaning there's no attractiveness. And that's important because, well, the loss of energy, it says that, now the other thing is that two particles more act like one particle because they stick together. And here is, I mentioned here with the McFlurry, so here is the temperature distribution with different gases, and this is the same temperature. This is all the same temperature. It doesn't give you the temperature. Okay, so, but you might notice, okay, so let me go to this chart. So the y-axis here is the number, x-axis is velocity or speed. Velocity is just speed with a direction. And you notice here oxygen is the heaviest, then nitrogen, then water. So oxygen is 32 grams per mole, 28 grams per mole, 18, 4, and 2. And the heavier ones, the distribution is narrow, and the lighter ones, the distribution is very wide. So that's one thing to note. And also, you can see here, really here at the origin, there are some particles that have no velocity. So how does that happen? Well, you have in gas, I only have two hands, but things are moving around, and what happens? They hit into each other. So you might have one moving along, and then this really fast one comes, bumps that one, and that one's flying away. Or maybe you have two fast ones that collide, and then they slow down. But then they get hit by someone else, and they move on. So the gases with all the collisions, there's a very wide range of temperatures going on there. And for the heavier ones, there's much less distribution between them. And the lighter ones is a much wider distribution. Why? Well, because of the heavier ones, the energy levels are more closely spaced. So, does this make sense? Anybody have any questions with this so far? And then you can probably notice there's something going on here. There's a peak. There's a peak for each of these. And what that peak is called, it's also the root mean squared velocity. So, root mean squared. It's the square root of taking the, let's just say the velocity. I don't know. In chemistry, we use U for gases. I don't know why. I would think V. But anyways, the velocity of the gas squared. Then you average that, and then you take the square root. Why would you square the velocity? Because velocity can be negative. How do you get rid of negative numbers? You square them. With the exception of an imaginary number, all squared numbers are positive. And there's no such thing as an imaginary velocity. So velocities have to be positive. They have to be real numbers. So squaring it will make them all positive. And taking the average of that and then the square root of that will tell you these peaks of the graphs. And okay, so now we looked at all the gases at the same temperature. Let's look at, this is nitrogen. And here's nitrogen at the top here at a cool temperature, 237 Kelvin, so 0 degrees Fahrenheit, Celsius. Here is at 1,000 Kelvin, here's at 2,000 Kelvin. And notice that the distribution just gets broader at the higher temperatures. So you still have some that are really low velocity, but you have much more lower velocity at the lower temperature. Not surprising. So what? Why do we care? So has anyone seen really old paper before? Like paper that's 1,000 years old. What does it look like?
Like kind of like the color's like kind of a little bit faded. It's like
Is it yellow-brown color?
yeah. Like,
It looks like it's starting to burn?
yeah.
Yeah, because it is. It's burning ever so slowly. So we're not going to talk about this till next semester, but Chemistry 162 we'll talk about kinetics. And there's something called activation energy. So as two things react, so if you have oxygen, so here's your textbook, and here's oxygen. If it wants to react with the textbook, oxygen's flying around, and what happens when it gets to the textbook? It slows down. Why? Because the textbook is made of mostly, it's glucose, basically. It's among other things, mostly sugar. Actually, paper is mostly sugar. So it's glucose, and glucose has an electron cloud. So as the oxygen also has electron clouds, it goes close to it, it slows down. And then it usually just bounces away. But if there's enough energy, what happens, the oxygen is able to hit there, has enough energy to overcome the repulsive barrier of the electronic cloud of the cellulose, and then it can react at the surface. So if you were to take something like your textbook or a paper, let it sit for a while, it will ever so slowly burn. But if I were to take paper and then like light a match and put it under the paper, it's going to be gone in like a couple seconds, right? Why is so a candle flame is about so that's about 550, 600 Celsius, so that's about 800 Kelvin. So that's closer to this. So why is it possible that I can use a flame to get rid of paper in a couple seconds, or I can throw paper and just leave it in air for a couple thousand years and it burns? Well, it's because there's this big fraction of gas at the higher temperature that has enough energy, and so those collisions, when it affects it, can start to burn it much more quickly. That is also burning paper is exothermic, so then it raises the temperature even more. So that's why paper burns ever so slowly, because a small amount of gas particles have enough energy to escape. Same thing with vapor pressure. So we talked about vapor pressure, that we have at higher temperature means that you have more fraction of gas in the vapor phase. Well, at a low temperature, so here, same idea with liquids. Liquids are going to have a distribution too. A small amount of the gas fraction at a low temperature has enough energy to escape. So for water, it's 40.7 kilojoules per mole. So there's enough energy for it to break those bonds. Then at progressively higher temperatures, a higher fraction of the liquid goes up into the vapor phase. So that's another reason why things are purported that the higher temperature has higher fraction in the gas phase. So questions with this so far? Okay, so yeah, chemistry is all interrelated. That's one of the things I like about it. Some people don't like that. Okay, but there's temperature, and oh, am I done for this section? I guess I am. Yep, done for that. Now I'm at 5C. Okay. I mentioned root mean squared velocity. Here is the derivation for it. But let's do an equation like this. What is the root mean squared velocity of oxygen at 25 degrees Celsius? And the equation is the root mean squared velocity is 3RT over molecular weight. So there's a couple tricks with this. So for the R, you have to use 8.314, and this is joules per mole Kelvin. Temperature 298 Kelvin is 25 degrees. Molecular weight of oxygen, it's 32 grams per mole, or 0.032 kilograms per mole. And raising something to the half power is the same thing as the square root. So let me talk about the units real fast. So that the D usually means dimensionality. So we have joules per mole Kelvin times 298, oh wait, I don't need the number, sorry, times Kelvin, all over kilograms per mole. So the moles cancel, the kelvins cancel, and we're left with joules per kilogram. So a joule, and if you haven't had physics yet, don't worry about it. You get these numbers. So I remember it as force is mass times acceleration. So mass is kilogram, acceleration is the second derivative. So it's going to be displacement per time squared. So kilogram meter per second squared, or mass times length displacement divided by time squared. That's force. And work, joules is work. Work is force times the path length. So a joule is a Newton meter. It's the force of 1 Newton over the length of 1 meter. So it's a Newton times a meter. So a Newton is kilogram meter per second squared. A Newton meter is a kilogram meter squared per second squared. So that's a kilogram meter squared per second squared all over kilogram. The kilograms cancel, and we're left with meter squared per second squared. The square root of meter squared per second squared is meters per second. So that's the reason why you have to use the R value at 8.314 joules per mole Kelvin because of the units. So the units have to cancel out, and that's why you have to use the molecular weight in kilograms per mole to get the units to work out properly. If you use different values, you get different. You'll just get the units won't match up. Is that making sense? Okay. So let's plug it in the calculator. Let's look at the calories in McFlurry. I'm getting hungry. I didn't eat lunch. But I went late. Could use a McFlurry right now. Oh. Put in the wrong number. There we go. That's something going way too fast. You know that trick? If you raise something to the 0.5 power, that's the same thing as the square root. If you want to raise it to the 1/3 power, it's the same thing as a cube root. Makes it easier on your... Anyways. So this is 482 meters per second. So that's really fast. A half a kilometer a second. Right? So that means in 2 seconds you've gone a kilometer, in 3 seconds you've got a mile. So 3 seconds, a mile in 3 seconds. That's moving pretty darn fast. And that's not even, although, I remember there's a distribution. That's in the previous slide. Remember you have the number and the velocity. It's a distribution of sorts. Well, I guess it's more like this. Right, so that's just there at the top, 482. That means we got lots of particles going much, much faster than that. And question I get sometimes is, that's faster than the speed of sound. So why aren't we having sonic booms going on right now from the gas particles? Well, it's because first of all, they're so tiny. Secondly, sound is a pressure wave. So the speed of sound is the pressure wave moving back and forth. Well, it's a longitudinal wave, so the vibrations go in the same direction. So if you have something really big, like a bullet or an airplane, yes, that'll cause a sonic boom, because then you can go through and it can break those pressure waves. But the gas particles themselves, because they also are what make up the pressure wave, those moving quickly will not break the sound barrier, if that makes sense. So, but that's really fast. I mean, something, I know it's in meters per second. Hopefully, can you imagine going somewhere where you can go a mile in 3 seconds? That'd be very fast, right? I'd get to where I'm going really quickly, unless I'm flying to somewhere far away like the moon. Right, so, okay. All right, we're looking at this problem. Let's go back to that. Here's the formula. You get the formula. You'll even get the different values of R, and you'll get well, I say that you should put it in kilograms per mole. And then putting in, using this value of R, you get 482 meters per second. You have to use that value because of the units. So questions with this? Okay. And so here is a typical molecule path, and it's kind of like a 3D pinball machine. If you've ever, I don't know, it might be. It's even too old for me. I didn't play too many. I didn't use too. I've seen pinball machines. I didn't really play with them though. But when I see gas in the container, like if I have like a cylinder of propane, what I really think in my mind is like pew 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 pew. It's like going around and it's smacking against the walls, all of that. So it's kind of like, and this is also where the pressure comes from inside a container. So pressure comes from the molecular collisions of the gas on the container. So like if you hit me with one molecule of oxygen, I'm not like, oh, that hurt. You know, maybe if you hit me with a baseball, that would hurt, right? Because it's really massive. But something like a single molecule of oxygen is going to weigh on the order of 10 to the minus 21 grams, right, or 10 to the minus 24 kilograms. That's nothing, you know. I wouldn't even notice. But then if you hit me with like 10 moles of oxygen, you know, that'll knock me flat on my butt, kind of thing. So same thing with a gas, with gases in a cylinder. So if you have a metal cylinder, the pressure of the gas comes from the collisions of the gas to the side of the container. And the other thing you might notice about gas containers, they're always round of some sorts. We have a propane tank outside this building by the parking lot. It's like shaped like a Tylenol, right? It's shaped like a pill. Why is that? Because if you have a corner, like say you have a sharp corner on something, then it's easy to crack along that corner. And if you ever do engineering, they call it the hoop stress. Because when you have gases inside a container, it pushes it makes the container expand. And that's why you have those rounded shapes on the containers, is so they can expand more easily. And that tells you a lot of things about gas. It's also why increasing the temperature increases the pressure, because now you have more collisions with the wall, so faster things moving. So if it's really slow, boo, 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 boo. It's like I said, you know, give a lot of energy, it's boo, 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 boo. It's like flying. It also has more velocity, which means it has more momentum. So it's like, hit me then, it's smack, smack. The higher temperature hits it harder. So more collisions with more force means higher pressure. And you probably notice if you take a soda can or aerosol can, you throw it in a fire, what happens? They blow up eventually. Because if it heats up high enough, it'll rupture the can. So, yeah, gases, they fly around with very dynamic paths. So, questions so far? Okay, and so what? You can have, this is called Graham's law of diffusion. And if you have a gas and you have a hole that the gas can go through, the gas will slowly, fuse through into the lower pressure, which is why we need to put air in our tires. So something simple like, you ever get the balloons, and over time, like the helium balloons, over time they lose their air, or like helium, I should say, lose their helium, because they go out through tiny cracks. So they'll escape through tiny cracks, and helium is small, so it's light. The lighter the molecule, the faster it'll fuse through. So even something like air, like you put air in your tires of your car, it'll slowly effuse through. That's why you have to fill your tires every once in a while. Because even here, like in Hawaii, we have the temperatures relatively constant. On the mainland, in the wintertime, you have to put air in your tires. And then springtime, you have to bleed the air out of your tires, otherwise they might rupture. And they might get too low, or they might not even flat. It lowers your gas mileage, the traction on your tires if you have deflated tires. So in the winter, you have to add air to your tires. The spring, you have to let a little bit out. kind of thing. But just sitting here in Hawaii, similar temperature year-round, the tires will ever slowly go flat. Why is that? Well, just little tiny cracks in the tire, and they'll fuse out. So why do we care? We can concentrate certain things this way. We can separate gases, and this is the Graham's law of fusion. The rate of gas A over the rate of gas B is the inverse square root of their molecular weights. Why is that? It's just the speed. It's the ratio of the speed. And again, why do we care? This is how we enrich uranium to make atomic bombs. So we don't necessarily use uranium anymore. We use uranium hexafluoride because uranium has a very high boiling point. What is a boiling point of uranium? So uranium has a boiling point of 3,927 degrees Celsius. But you can react it with fluorine to make uranium hexafluoride, and that has a boiling point of on the order of 35 Celsius. So it's much easier to do that. So what? Why do we care? Well, if you follow the news, Iran, they say they're not making nuclear weapons, but they found enriched uranium past 20%. So although that's not enough to make a nuclear bomb, you need to have on the order of 90% or better to have weapons grade, more likely on the order of 98%. So civilian nuclear plants here in the United States, we typically use 3 to 9% enriched uranium. And the fuel, the odd number is fissible. It's able to you can use it as a nuclear fuel or for weapons. And nuclear bomb. So on the big end, they're probably maybe twice the size of this desk, but at least the first stage of it, they can be, so it's about 50 kilograms of uranium. It's about this big around, so like a medium-sized beach ball of uranium, maybe even smaller. It's actually more like the size of a football. I'm sorry, it's 50 kilograms. I don't know what the density of uranium is. So 50 kilograms of uranium, about this much uranium. If you go to a civilian nuclear power plant, the core of the power plant is probably on the order of about 8 times the size of this desk. So it's like 2 desks, it's like 2 desks here, and then 4 to 8 times, depends on how big the nuclear power plant is. But if you go to a nuclear sub, the core of a nuclear sub is about the size of a trash can. So, and they use weapons grade uranium in that. So what's the difference? Well, in a submarine, you're confined by space. Having a nuclear power plant, having the core being really big, that means you'd have an engine room really, really big to have that. And space is a premium, so they concentrate down to weapons grade. And if you have a civilian nuclear power plant where you're not confined by the size, you can just have a dilute fuel source, which is also nice because a nuclear power plant is not going to explode like a nuclear bomb. It can't, or at least it cannot explode like a nuclear bomb, but a Navy vessel could. But civilian plants cannot. But you're like, what about Fukushima? That plant exploded. It got hot, and they used water inside of that, and the water broke down to hydrogen and oxygen. Hydrogen, oxygen plus heat makes water vapor and explosions. That's how Fukushima blew up. It wasn't a nuclear detonation. It was a chemical detonation, just from the heat from the water. Okay, so my point is either Iran hates money and they're galactically stupid, or they're making nuclear weapons because of the fact. So I mean, if you only need 3% to have a nuclear power plant that generates all electricity that you want, why would you enrich it past 20%? Because, well, you enrich past 20%, that means you need to have a smaller core that gets hotter. That means more temperature controls, and it's more likely to explode. So you have to have more safety on that. So you can have a bigger plant that requires less money to run, less money to get the fuel, or you can have a smaller plant that's more dangerous and more costly. I mean, of course they're making nuclear bombs. They're not dumb. You know, what else will they be doing with it? So, but we'll go through that example later. So let's use this for a problem, Lagrange's law of fusion. So an unknown gas diffuses at a rate that's 4.62 times that of nitrogen gas. So the rate of A over the rate of B, so the rates of nitrogen all over the, we got it backwards. Rate of unknown. Jeez, I can't spell it. Rate of unknown over the rate of nitrogen equals 0.462 equals the square root of 28 over x. So then you square both sides. So 0.462 squared equals 28 over x. And then x equals 28 over 0.462 squared is my. Sometimes my students yell at me that I go too fast. I'm just flipping x here. This x there, multiplying both sides by x, and then I can take this and put it underneath like there, like that. Is that okay with everybody, or do you want me to break it down more? Okay, so then, if I remember, this is 131. 28 divided by 0.462 squared. Yep, this is 131. 131 grams per mole. And so this is probably xenon. The xenon is 131 grams per mole. So, yeah, so questions with this? This also explains why we don't put helium in our tires. So helium it's not too expensive, but it's more expensive than air. I mean, air is pretty cheap. I know at Costco they put nitrogen in your tires. So if you ever want to have, it's a little less reactive, I guess, a little lighter. But why don't they put helium? Well, because it diffuses out too fast. Okay. So, the questions with this? All right. So uranium hexafluoride 238, uranium hexafluoride 235. You can infuse that to enrich the isotope. How much faster does 235 infuse than 238? And they usually use centrifuges for this, so like a big centrifuge. So if you ever are somewhere, and also this stuff, the uranium hexafluoride, it's yellow. It's a yellow color. It's sometimes referred to as yellow cake. So if you are somewhere and there's this yellow powdery stuff, and have you ever been? Anyone ever been to a brewery before? No one has. There's big steel tanks. So if you ever been to somewhere, it looks like a brewery, or maybe like a well, it would look more like a brewery than a refinery. Refineries, first of all, they smell. Has anyone ever been to a refinery? They smell really bad. They smell like sulfur and gasoline all rolled in together. But there's a lot of distillation columns in them. But if you ever, like a brewery has a bunch of stainless steel tanks, and the centrifuges, usually they sound like a kind of sound. And if you see somewhere that looks like that, you might be in a enrichment plant. So don't just like, oh, that's a nice brewery, and just leave. leave the country. Okay. Much faster does this work? So we have, so it's going to be 238 plus 19 times 6 all over 235 plus 19 times 6. Screw that. Because it's the mass of B over mass of A. So 1.004. I know I'm not letting you guys play, but I'm feeling selfish today. I'm doing my own math. So only a fuse is at 0.4% faster. So that's why it's hard to make nuclear bombs. At least using uranium. It's much easier. Well, uranium bombs, they're real easy to make, like if you have the materials. So if you have two subcritical masses, you can just push them together. The bomb they dropped on Hiroshima in Japan, there was a cylinder that had a open part in it, and then you had a bullet-like thing that went into the cylinder. It just had an explosive that shot it into the cylinder, and then that caused the detonation of about 18 or 19,000 tons of TNT. Plutonium bombs. So the first bomb they ever detonated was not in Japan. It was the Trinity test in New Mexico, and there was a plutonium bomb. Also, Fat Man, the one they dropped on Nagasaki, was a plutonium bomb. Plutonium has its spontaneous rate of fission is much higher than uranium's, which means, so the reason why the uranium works has a low rate of spontaneous fission, and it releases neutrons, and the neutrons then can split the atoms. Plutonium fizzes too quickly, so you can't do it by two balls being smushed together, which for plutonium you have to have a sphere and compress it down. Critical mass for plutonium is on the order of 5 kilograms. So uranium is about 50, and plutonium is about 5. So a plutonium bomb can be as big as a softball. So it can be this big to have a nuclear bomb, whereas uranium is going to be a much bigger bomb. And you have to separate it too, because you can't get it too close, because it'll start to react. So and plutonium makes better bombs too. That's the thing, plutonium. So North Korea is trying to build nuclear weapons. They have enough material to make them. It's debatable whether or not they had some explosions, but they weren't very good ones. So they claim to have a hydrogen bomb. I don't think they have a hydrogen bomb. I think they have what's called a boosted fission device. It's where you put tritium in with the nuclear material to get a slightly higher yield. So that's my own opinion. But I used to work as a nuclear scientist. So not non-classified, of course. Otherwise, I wouldn't be talking about what I'm talking about right now. So the nice thing about plutonium, though, is that you can separate it out chemically, whereas uranium you have to separate it out an atom at a time using centrifuges. There's another technique you can use using lasers. So that's another way you can hit it with lasers, and then you can vaporize the uranium and then draw it out that way. So, but either way, it's plutonium is easier to make and extract it, and it makes better bombs. So, although it's harder it's a more difficult problem to compress it down to the critical mass. Whereas uranium, you just take 25 kilograms and shove them together and they explode. So, all right. Although it's a little outside of this class, at least for this semester. Nuclear chemistry is next semester. Anybody have any questions about nuclear chemistry? I love talking about nuclear chemistry. Nope. Okay. Too bad. All right. So I'm not going to test you on this. So you're not going to be tested on this, but I'm going to talk about real gases. So, and the molar volume. So an ideal gas has a molar volume of 22.4 liters. And you can see the real gases, except for helium, is exactly at that. And then they have about that, but slightly less. And then hydrogen a little bit more. So real gases do not necessarily behave like ideal gases. So what is going on here? Well, these other gases, they have attractions for each other. And because of that, they're a little more sticky. And they actually put a volume less than is expected. Helium is about the most stoic element there is. Even so, liquid water, for instance, the distance between two water molecules in liquid water is about 300 picometers. And solid helium has a distance of 500 picometers. So, and usually when things become solid, they get more compressed. Water is weird, that the more common form of the solid. Now, there are forms of solid water that are more dense than liquid water. And you can find those on the bottom of the ocean as well. But the most common form, at least at this temperature, the most stable form at this temperature and pressure, is less dense than the liquid. So water is a weird substance. But helium, we argue whether or not helium actually has a liquid or gaseous phase. We don't really know. So, or at least we argue about if it does or not. Hydrogen, why is it slightly bigger? It could be because it breaks apart. So it might break apart into two hydrogen atoms to give it even a more massive volume than you expect. So what at the effect of non-ideal behavior, effect of the particle volume. So if you at really high pressure, remember that the kinetic molecular theory said the particle itself has no volume. But if you start to increase the pressure, suddenly the particle, the fact the nucleus and the electron cloud, suddenly the size of that matters. Atoms aren't very big, right? But if you have a huge amount of pressure and they get really, really close to each other, they're going to start pushing back. And that's where this exception from the non-ideal behavior comes from, is that under high pressure that the gas particles start to push back. And then the effect of intermolecular forces at temperature. So, and at low temperature, so this is opposite. The high pressure, the volume is I always thought you'd kind of opposite. At high pressure, the volume is bigger than you'd expect, but then at low temperature, the volume is less than that. Why is that? It's because it's sticky. So when you have, xenon is a very good ideal gas, but so xenon has a very large cloud to it, has a very large electronic cloud, and we'll learn more about this next semester, but the electron cloud can move one way or the other, and you can get a slightly positive and a slightly negative end, and then those two xenon atoms can have an attraction for each other. So they spend more time together, and it looks like, so it seems like the gas particle, instead of being 2 particles, it's like 1. And so because of that, then the volume then the volume would decrease that way. So that's the attractiveness between the particles, so the low temperature. At high temperature, though, if they're moving too fast, they're not able to stick to each other. So ideal gas law works really well for low pressures and high temperatures. And right now, we are at considered low pressure and a high temperature. And this is the van der Waals equation. And I gotta tell you, this is a really bad way to do real gases. So if you ever have to deal with real gases, there's better ways to do it. There's something called K's law, where you have PV equals a fudge factor, like a Z nRT. So and then they have data tabled for various temperatures and pressures. That just takes everything and sums it into one lump sum. It's called a lump sum approximation. I'll talk a little bit about it next semester. That's an easy way to do it. You can even look up the values you need to. There's equations that you can use. There's something called the Antoine equation. There's something called the Cox chart, COX charts, and you can look at all the data for gases on that. So you can just use real data instead of calculating things. But you can use the van der Waals equation, and this equation doesn't even work that well either. You can say I don't like it. Instead of PV equals nRT, you have P plus some A term over N over V squared times the volume correction factor for the particle volume there. Why, if it's so terrible, why do I talk about it? Because it explains what an ideal gas versus a non-ideal gas is. In practice, it's much easier to use other ways, but this explains what the nature of the gases are. And the other thing, if you look at this equation, you have n on both sides of the equation, which means you have to solve this iteratively. Have you ever solved something iteratively? It's very difficult. Okay, and here are the constants for the various gases. And you can see helium just doesn't care. And all the rest of them, the bigger the molecule, the more sticky they are and whatnot. So questions with real gases that you're not tested on? Okay. All right, and now we're moving to thermodynamics. So if you ever take a speech class, I always tell you don't apologize to the audience and don't say you don't like things. And sorry guys, I need to apologize and tell you I don't like thermodynamics. I never did. I'd rather study stoichiometry or teach it than thermo. I hate thermo. Arrgh. But anyways, my students tend to love it because it's very straightforward. Thermo is very straightforward. And so we're going to do 2 chapters of thermo, not this class. We're going to do 1 chapter here and another chapter in Gen Chem 2. The difference between now and Gen Chem 2. In Gen Chem 2, we're going to talk about entropy. Entropy is disorder. And we're also going to talk about free energy. So 2 concepts. But we're going to talk about the first law of thermo now. But if you know the second law is entropy of the universe is always increasing. And then there's a third law. Does anybody know what the third law is? It's almost like a Jeopardy question. It's trivial. Anyone know what the third law of thermodynamics is? It's a perfect crystal has 0 entropy at absolute 0. It just says that entropy is proportional to the number of states. It's the natural log of the states. And if it has 1 state, a perfect crystal has 1 state, so the natural log of 1 is 0. So it has to do with the definition of logarithms. It just defines what entropy is. Anyways, but that's next semester. And like I said, third law is no consequence. It's almost like it's trivia. It's trivial knowledge. Anyways, energy. So let's talk about energy. Energy is the capacity to do work. Well, that's what chemistry definition is. And I've been eating chocolate, so I'll eat some chocolate now. Give me a little more energy. Means I have the capacity to do work. My brain runs off of sugar, right? So a little bit of energy there. I can also jump around. and go swimming and do something else with his work, with his energy, right? And real simple. Well, the unit for energy is joule, at least the SI unit. And a couple types. Kinetic and potential energy. So the old high school physics definition. This textbook has potential energy. Is everyone awake? Yeah. And if I drop it, it will turns to kinetic energy. So the potential energy has transferred to kinetic energy. And what about that? The law of conservation of energy states that energy is neither created nor destroyed. And that is exactly what the first law says. Oh, and kinetic energy is 1/2 times mass times velocity squared. That comes in later. So the first law, according to chemistry, is the change of internal energy of the system is equal to its work plus heat. So W is work, Q is heat. There's more terms. I mentioned so gravitational potential energy. You can add that to the first law of thermodynamics. So if you take an engineering class, they'll add a couple more terms. So this book, the first law of thermo, there's gravitational potential energy here, and then it decreases as it drops. Which actually, when we turn on our water faucets, that's the first law of thermodynamics. You have water that has potential energy, gravitational potential energy, and then you open up the tap, it flows downhill, so it loses its potential energy. And that energy then goes from potential to kinetic energy. Flows out the tap. Okay, so a couple things with this. So I have energy. So internal energy system. So this is known as path independent, also known as an exact differential. Is anyone in Calc 3 or 4 has taken Calc 3 or 4? Have you talked about exact partial differentiation?
No, I'm like that.
Okay. So if you have a function that it's differential with respect to one variable and the order is the other, here I'll do it this way. If you have a function that the partial differential is equal to this way, so if you do by one variable, you're going to do it by the other, that is referred to as a mother function, and also said exact differential, also known as a state function. So, and then the state function is path independent. If this is not true, that is known as being path dependent. So the internal energy of the system, this is path independent. This is a state function. So, or mother function or exact differential, whatever term you want to use. Work and heat are path dependent. So what do I mean? I can take a gallon of gasoline and I can put it into a drum and I can light it on fire and just let it burn. And I can get no work out of that, and I can get whatever amount of heat, a million joules. It's going to be more than that, but 100 million joules. 100 million joules of heat out of that. Or I can take that gallon of gasoline, I can throw it in my car, and the energy of the system, the gasoline, the energy that's in the gasoline, it can all go to heat and no work, but the change of energy is the same if I burn a gallon of gasoline that way. If I put it in my car and I run the car, I get about 20% of that as work, so I would get on the order of 20 million joules of work, and then the rest in heat, 80 million joules. So you ever been in cars, the car engines, they get hot because you're only getting, the thermal efficiency of a car is only on the order of about 1/5. Diesel engine slightly higher, is on the maybe 25%-ish. Then or I could take it and I could throw it into a hybrid car and I could maybe get, I don't know, a third of it by work, and then the rest heat. But either way, if I'm using a gallon of gas, the work plus the heat going together is always going to be the same number. It just depends on how I'm using the energy. Same thing for us in the human body. I just had some sugar from the Hershey's thing that I left over from your test, and I could burn that. We can burn food. It's pretty easy. You ever use Doritos to light a fire? It burns really fast. So food can burn. Food burns. It can burn outside or it can burn inside of us, right? So you can burn it just like high temperature and then oxygen, or you can use the enzymes inside of our mitochondria to form ATP and then use the ATP to do stuff. But even using the ATP, we humans were said to be about 1/3 efficient. So if a car is 20% efficient, we're 1/3 efficient. But I don't really. That's if you calculate out work. I never really liked that term because the efficiency with humans, because we do other things. I mean, we make ATP, adenosine triphosphate, and we do that to push our certain biological processes. We're using the kind of a springing action of the phosphate groups to push things to certain places. But it's not like if you like say you gave me a couple candy bars and you told me to haul a bunch of stuff up a hill, take a wheelbarrow and pull it through the logs and tell me to go climb it up a hill, I would be 33% efficient. But I mean, our bodies do other things too, right? I mean, I would be tearing my muscles and I would have to repair those muscles using food. And besides the other thing, I mean, I have to run my organs, right? My brain, my heart, my lungs. They all have to run. So that's not I never really liked that analysis with macroscopic work. Anyways, so then the next thing is with the first law with thermo, and the hardest thing to do is to figure out what your system is. And we also have directions. Energy flowing into your system is positive. Energy flowing outside of the system is negative. So it depends on what you define your system at. That's where the sign of the energy happens. So if I grab an ice cube out of my freezer and I hold the ice cube in my hand, so if my hand is the system, I'm giving energy to the ice cube. So my energy, the system is my body, my hand, whatever part of me holding ice. The energy going out of the system is a negative. So I'm losing energy, or the energy is a negative direction as I'm holding something cold. If your system is the ice, the energy is flowing into the system. That's a positive direction. And also for chemical reactions, positive energy is known as endothermic, and negative energy is known as exothermic. So endo means inside, exo means outside. So we'll talk more about that later, but I wanted to try and bring this all together. So thermo, we're talking about the first law. First law is the conservation of energy. And for chemical reactions, the internal energy of the system is equal to the work plus heat. So here's a simple first law. If our change of internal energy is 50 joules and the work is 20 joules, how much heat is evolved? How many think it's 50 joules? How many think it's 30 joules? How many think it's 20? I think it's 10. Oh, you guys aren't getting it. Okay. So delta E is equal to work plus heat. 50 is equal to 20 plus our unknown. So maybe think A, maybe think B. I have more people going for B, but not everyone's playing. You guys, to me, it's obvious that it's 30. Are you guys stuck on something, or are you is Facebook more interesting than? which is it probably is. It's thermo. And you're not going to offend me now. I'm like, we're talking about quantum mechanics. I'm like, come on, it's quantum. The thermo. Whew. But yeah, it's just. Does anyone have any questions with this? I tend to think this is kind of obvious, though. You just don't want to play. Okay. People don't want to play with me today. Okay, nutritional calorie. So if with energy units, so if you want to know what a calorie is, a little calorie is energy for 1 gram of water, 1 degree Celsius. So a calorie. So the unit calorie is the energy it takes to raise 1 gram of water 1 degree Celsius. Does anybody know what a BTU is? Have you ever heard of a BTU before? It's a British thermal unit. So anybody want to guess what a British thermal unit is? It's the amount of energy it takes to raise 1 pound of water 1 degree Fahrenheit. And if you ever bought a air conditioner before, they say it's, this is a half-ton air conditioning unit, or is a 3-ton air conditioning unit. Like, they're not talking about the weight of the air conditioner. I mean, they are heavy, but they're not, a unit is like a half-ton unit is probably about 50 pounds. It's not, it's not 1,000 pounds. It's the number of BTUs. A TONNE BTUs is 2,000 BTUs. So a half-ton means it's 1,000 BTUs of heat it can absorb, and I think it's an hour or something like that. So, so a calorie. Let's go back to the metric system. A calorie is 1 gram water, 1 degree Celsius, and a nutritional calorie. And if you ever look at a nutritional calorie, it's capital C. It's because it's actually a kilocalorie. So it's the energy it takes for 1,000 grams of water or a kilogram of water 1 degree Celsius. So your 100 calorie chocolate bar, so I think 2 of those or 3 of those, I think it's equal to 200 calories or something like that. So your 100 calorie chocolate bar means you can raise 100 kilograms of water 1 degree Celsius, or 1 kilogram of water at 100 degrees Celsius. That's a lot of energy, right? I mean, you ever tried to boil water before? That's a lot of energy. So food, not surprisingly, food is jam-packed full of energy. And a joule, I'll show you later, a joule, Newton meter, kilogram, meter squared per second squared, there's 4.18 joules in a calorie. So if you ever go to Europe or travel some places, you look at food nutritional things, I do that. I look at the nutritional labels of food. I don't know if it's one of my hobbies or something like that, especially when I don't speak the language of the place. I'm trying to figure out what I'm eating. Sometimes they give it to you in kilojoules per something. Like they'll say the energy is kilojoules, and if you want to know how many calories it is, just divided by 4.18, divided by 4. That's what I do. I used to live in Hungary, and I remember that they give the energy and they didn't give calories, they give it in kilojoules. So, okay, we're going to talk about heat, and heat is equal to this first line, heat capacity. C is heat capacity times change in temperature, or mass times specific heat capacity time change in temperature. I'm using the dots. I got to be careful as if you're in Calc 3. That's not the vector dot product. That's multiplication. So, okay. So what is heat capacity? What's specific heat capacity? Let me back up to childhood. I remember whenever I went to go to the pool in the summertime. I remember if you have a seatbelt that's shining in the sun, it gets really hot. And if you have a water bottle that's sitting in the sun, it doesn't get very hot. But if you have the seatbelt, the middle part of the seatbelt, I used to take it and sometimes put my arm oh, that's so hot. They're like, but it's not hot anymore, right? So metals have very low heat capacity, which means is that a little bit of energy makes the temperature go up really high, really fast. Water, on the other hand, has a very, I'm sorry, metals have a very low heat capacity. Water has a very high heat capacity. And which means you put energy in the water, the temperature of water only goes up a little bit. And likewise, if you draw energy out of water, the temperature goes down a little bit. Which is why you can take a spoon. I told you before that if you have an insect bite and you want to get rid of the itching or the venom, or so you take a spoon, you put it into hot water, and you put the spoon on yourself. That's because you can get a lot of energy in a really small area, and it'll decrease the temperature real fast. That's why I tell you, like, oh, don't stick your arm in boiling water. That'll get rid of the venom, right? Well, it will, but it'll get rid of other problems too, or have more complications. So heat capacity then, that's for the whole whatever it is you're looking at. It's kind of like mass versus density. So if you have a specific heat capacity for something, though, specific heat capacity for water, it's the definition of a calorie. Specific heat capacity for water is 1 calorie per gram degree Celsius. So, or 4.18 joules per gram degree Celsius. So, which means if you have 100 grams, that means the heat capacity is 100 calories per degree Celsius. So this is the big one, and this is like the smaller specific one, like density. So we'll go through some problems like that later. All right, and let's do this. So suppose you find a penny before 1982 in the snow. It's obviously not written for Hawaii. How much heat is absorbed by the penny as it warms from the temperature of the snow, which is -8 degrees Celsius, to the temperature of your body, 37 degrees Celsius? Actually, your hands, they're usually not at 37. The core of your body is 37. Your extremities tend to be less. And mine's probably pretty low right now. I'm probably at 33 or 32. I've noticed that if you haven't eaten, your body, your tan temperature goes down. I do a lab for my I'm not teaching the class right now, but for the Chemistry 100, I call it Chemistry for Poets. It's non-STEM major chemistry. One of the labs I do is I have students measure their hand temperatures and say, who's the hottest student in this class? We'll scientifically determine who the hottest student is. And if I have the lab after lunch, people's temperatures are much higher, I've noticed. So, before, at least, I usually get students not right after breakfast, right? Because usually students eat breakfast at home and then travel. So it's rare that I get a student that's going to eat a bunch of food and then come into class, especially a lab. Anyways, so hand temperature is probably not 37. I guess you could put it in your mouth. That would be about 37, but who'd want to stick a penny in your mouth that you found in the snow? Anyways, all right. So, how much heat absorbed the penny? Okay, so our heat is equal to mass times specific heat capacity times change in temperature. So, mass is 3.10 grams times specific heat capacity of copper, which I don't know, and delta T. So change is always final minus the initial. So final is 37 minus a minus 8. Did I put the... Okay, I'm glad I brought my textbook. What is the heat capacity of copper? That I don't have memorized. Anybody know the heat capacity of copper by any chance? Heat capacity of copper is 0.385 joules per gram degrees Celsius. And this is degrees Celsius. So This one is just 3.1 times 0.385 times 37 plus 8. Okay. .7 joules. And that's actually not a lot of energy. So we'll get to chemical reactions. You'll see it's huge. Energy is in really, really big in other places. But this is not that much energy. But do you see how to do this? The heat is equal to the mass times specific heat capacity times change in temperature. And the energy is positive because it's going into the system. The penny is absorbing energy, so the energy is in the positive direction. That's the other thing I do is whenever I'm done doing a thermal calculation, I always come back and say, does this make sense? Am my energy flowing the right way? I tend to do these problems much more intuitively in that regards because I always if you've ever made the mistake where you've missed a negative sign somewhere when you solve an equation and it just mucks everything up and then you get this weird answer that makes no sense whatsoever and then you have to go back like, oh, what's a negative sign there? I'm always very weary of that. So I'm always in my mind, I'm thinking like, where's the energy flowing? Because that's what the negative is. It's with the direction of the energy flow. So I always kind of mindful, like whenever I'm done with a problem, I think, okay, where's my energy going? Is that the right way to do it? So that's why I'm looking at the answer and saying, is that the right energy flow? And it is. It goes from cold to hot, which means it absorbs energy in a positive direction. So I'm good. But questions on this and my logic and as I talk about this? Okay, here's a much harder problem. Oh man, we're not going to have time to solve this one. Yeah, we're definitely not. I think we got 4 minutes. No, I think it's a good place to stop. Anybody have any questions? All right, we'll pick up here on Wednesday then. And I will go ahead and stop the recording.